Welcome back. In this lecture we will add traction force from the powertrain and see how to calculate the total net force on the vehicle. Newton's second law can then tell us how much the vehicle will accelerate with a certain traction force. We now will look at how the powertrain influences the vehicle. The powertrain applies a traction force to the vehicle. Most of the time it is positive, which means that it is acting in the driving direction of the vehicle, but it can also be zero and negative in some situations. The force is distributed on all the driven wheels, but we only need to consider the total traction force. Here it is illustrated as acting on the front wheels of the car. Once we know the traction force and all driving resistance forces, we can calculate the total net force in longitudinal direction. Newton's second law tells us that the net force is equal to the vehicle mass multiplied with the vehicle acceleration. We can use this to control the acceleration by controlling the net force. To do that, the powertrain needs to produce a traction force equal to the rolling resistance plus aerodynamic resistance plus the vehicle mass times the desired acceleration. And once we get an acceleration, with time the speed will also change. So the driver is controlling the speed only indirectly by controlling the force from the powertrain and thereby the acceleration. We now assume that the traction force is 750 newtons at a speed of 50 kilometers per hour. Then, when we know the traction force, the net force can be calculated as the vector sum of traction force, rolling resistance, and aerodynamic resistance. The vector sum is the net force, and from that we can calculate the acceleration, which is in this example 0.32 meters per second square. Since the net force acts in the driving direction of the vehicle, it leads to an acceleration. Now we will show how the same analysis can be illustrated in a force-speed diagram with a curve showing the rolling resistance plus aerodynamic resistance. In this situation, the vehicle is driving in 50 kilometers per hour. We take the vector sum of aerodynamic drag force, rolling resistance force, and the traction force from the powertrain, in this case plus 750 newtons. The result is the net force, and it is equal to the vehicle mass times the acceleration. Notice that the acceleration is proportional to the difference between traction force and the road resistance curve at the actual speed. All the force vectors should of course be at 50 km per hour, but for clarity they have been plotted side by side. If we keep the traction force constant, the speed will increase. And when the speed increases, the aerodynamic resistance will also increase. If we now calculate the vector sum of the forces, we get the net force. Notice that this time it is a little smaller than at 50 km per hour due to the increased aerodynamic drag. In this speed, the 750 newtons of traction force will lead to an acceleration of 0.24 meters per second square. The situation at 75 km per hour can also be analyzed in the force-speed diagram. The vector sum with the same traction force of 750 newton give a net force at 75 km per hour, which leads to a little lower acceleration since the total driving resistance is higher at 75 than at 50 km per hour. If we want to keep accelerating to 100 km per hour, we can keep the traction force at 750 newton. The speed increase, and that leads to further increase in aerodynamic drag. Once we reach 100 km per hour, we want to stop accelerating and instead keep the speed at 100. Then the driver has to decrease the traction force, such that it is equal to the driving resistance forces. and the result is a net force equal to 0. And with no net force, the acceleration stops and then speed is constant. Notice that the traction force is not set to 0, but it has to be positive to balance the sum of the driving forces. In the force-speed diagram, we can see that the traction force is kept constant during the acceleration. Since it is bigger than the driving resistance force, the acceleration will continue. Once 100 km per hour is reached, the traction force is reduced to perfectly match the driving resistance at 100 km per hour. The vector sum of the forces becomes 0, so that the net force becomes 0, and then there is no longer any acceleration. As you have seen, the rolling resistance plus aerodynamic resistance is very useful for analyzing the force the powertrain needs to produce. This diagram shows how the sum of those forces change with speed for one car. Since a vehicle much of the time drives at a rather constant speed on a rather flat road, this curve shows the force which the powertrain will produce a large part of the driving. Remember this curve and what it represents, as it will be used many times when sizing and analyzing powertrains. In this lecture we have shown what happens when we add a traction force from the powertrain. The net force is the traction force minus the running resistance forces. The acceleration can be calculated using Newton's second law as the net force on the vehicle divided by the vehicle mass. So, now you know the basics of forces and how they influence the acceleration of a vehicle. Check that you have understood these basics by doing the following exercises before we go on to discuss deceleration and how the driver can control the vehicle speed.